Okay, welcome back. This is exponential functions. So last lecture, we refreshed on exponential properties, exponent laws, all that fun stuff. So today we want to get into exponential functions. And the definition of an exponential function is, first, if the equation looks like f of x equals a to the x, this is your basic exponential function, where the base has to be greater than 0 and the base can never be equal to 1. This is an exponential function with base a. Okay. Then the domain of the exponential function is from negative infinity to infinity. The range of the exponential function is all positive numbers from 0 to infinity. The graph of the exponential function will pass through the point 0, 1, and all exponential graphs are continuous with no holes, no breaks, no jumps in the graph. It's one continuous curve. Okay. The x-axis is the horizontal asymptote. Remember that the horizontal asymptote is a line that we approach but may never touch. Okay. And then, if the base of the exponential function is greater than 1, then it's an all-increasing function. If the base is between 0 and 1, then it is an all-decreasing function. Okay, those are properties of an exponential function. Now, let's go ahead and graph the given exponential function. F of x equals 2 to the x. We want to state the domain, range, and the horizontal asymptote. So we are going to graph 2 to the x power. So I will show you how to plug those in your calculator. Okay, so now I'll screen share mine. I'll go to the TI Smart View. Let's see. Yes. Okay. And again, click the table button. You're going to add function, or you'll get the y equals, one of them. Let me actually do the simpler output one. Let me see. Let's see, table, nope. How about this one? That's better. Okay, so when I hit table, I get that, and we're graphing 2 to the x. So I type in 2, hit the little caret button, hit x. Enter, 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 make sure it's still on ask x, enter, and now let's type in our numbers. -3 gives me 1/4. So -3 gives me 1/4, and again, if you want to convert this to decimal, just hit the little double arrows there, and it converts it to decimal. Okay, why is that screen so big? That's probably better. Either one. Okay, so we get 0.25 for -3. So 0.25, and then I'll type in -2. Oh, that was -2, oops, -3. Nope. I keep pushing all the numbers. There we go. -3. That's super weird. I guess I'll type them in here. -3. There we go. That's 1/8, which gives me 0.0125. So 0.125, -2 was 0.25. So again, -2 was 1/4. -1 is 1/2, which is 0.5. 0, let me go back up. 0 is 1. 1 is 2. 2 is 4. So 1, 2, 4. And 3 should give me 8. Okay, that's how we type them in the calculator. Other than that, if you're not using the table feature, then you can just type it in as 2, hit the little caret button, type in -3. Then you can convert to decimal, 0.125. Do it again, 2, caret, -2, 1/4, decimal number, and just keep doing that for the rest of the numbers. Okay, perfect. Okay, back to the screen. Go, share, 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 all that good stuff. There we go. We're back here. I have my numbers, so let's go ahead and plot. Let's see how big that's perfect. Okay. Actually, I'll plot with that first. So at -3, you're at 0.125. So that's basically 0.13. So you're just barely above the x-axis. Then at -2, you're at 0.25. Not much higher than the last one. Then at -1, you're at 0.5. A little higher. And then at 0, we are at 1. At 1, we are at 2. At 2, we are at 4. And then at 3, we are at 8. Then connect. So my graph is going to look like this. There we go. That is the graph of 2 to the x. And we say the x-axis is the horizontal asymptote. So I'll draw that. This little dashed line of x equals 0, which is the, not x equals 0, y equals 0 is the x-axis. It's a horizontal line, that's why it's y equals 0. And no matter what x value you plug in that's at towards -infinity, you're going to get really close to a horizontal asymptote. You're going to get really close to 0, but you're never going to touch it. So, and you can prove that by your calculator. You can type in 2 raised to the -100, and you're going to get a decimal number, like 0.0000 something, probably like 0.0005, and it's still not 0. So that means it'll never, ever, ever touch the x-axis. It will never, ever touch 0. Okay. With that being said, from the properties above, the domain of the exponential function is always -infinity to infinity. The range is 0 to infinity. And the horizontal asymptote is y equals 0. That's it. Okay. Rules of exponents, you guys remember these? We learned them last time. So a to the x times a to the y, that is the same base you add your exponents. A to the x raised to the y. An exponent raised to an exponent means you multiply your exponents. The 0 power rule, anything to the 0th power is 1. A to the x over a to the y, same base over each other. You subtract your exponents. This one is product to power. A times b raised to the x means a to the x times b to the x. And next is your negative exponent rule. A to the negative x equals 1 over a to the x. So remember, anything with a negative exponent, you can change into a fraction. Okay, perfect. All right. So for now, all we want to do is evaluate these functions in our these expressions in our calculator. So let me go ahead and go back to my calculator screen. Stop sharing, share my screen. There's me, there's that. Share and clear. Now let's type all these in our calculator. Good calculator practice. Okay, so the first one is 4 cubed, 4 to the third, 64. So we get 64. 2.5 raised to the 7.1. And we're going to round to 2 decimal places, 668.92. Next is 3 raised to the -2. You get 1/9. Or again, if you wanted to convert that to decimal, hit the little double arrows. You get 0.11 repeating. All right. Next one is 1/3 squared, parentheses, fraction button, 1/3, close parentheses, square it. Hit enter. Again, you get 1/9. Or, again, 0.11 repeating. Okay, let's say you don't have a fraction button. Then, parentheses, 1/3 squared. There you go, 1/9. Or 0.11111111. Stop that, come back here, again, share, me, share, screen, OneNote, bam. There you go. All right, let's keep going. Okay, next, we come across the definition of the number E. Yes, I said the number E. It is no longer a letter to you, it is a number. Okay, so E, to keep it simple, is called the natural number. The number E is used to determine the growth rate of bacteria, animal, people, money. It determines the growth rate of any population. So E is called the natural number. That's what we use it. And we definitely use it for business because E can tell us how fast our money is growing continuously. So that's what E is. If you want to look up, if you want to know more about E, go ahead and do a Google research on it. It's really cool. For now, let me confuse you a bit. E happens to become, so I'll show this first. So E is approximately this run-on decimal number down here. 2.71828182845 yada, 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 yada. It's kind of like pi. Pi is 3.14 da, 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 right? So E is an irrational number just like pi. And where we get this value for E from is from this lovely expression right here. 1 plus 1 over h to the h. We say that as h gets infinitely larger, this expression starts to become the number E. Look at all those arrows. And the best way to represent this is by the chart over yonder. So we see that my h values are getting increasingly larger towards infinity, right? All of these values are headed towards infinity. And as h gets increasingly larger and larger and larger, we see that this expression, 1 plus 1 over h to the h, starts to approach a similar number. 2, 2.59, 2.7, 2.71, 2.718, 2.7182, 2.7182, 8169. So no matter how large the number gets, we are still going to get this number, 2.7182, which is what we say E is approximate. That is the approximate number for E. So this is where it all comes from. My notes now look like a football play. So I just wanted to show you where we get that number from. Now, all you have to do is work with it. You don't have to care about any of this unless you really want to. I think it's pretty cool because, like I said, it's called the natural number. It can determine the growth rate or decay rate of anything. So, super cool. All right. So for now, we just want to do these simple calculations. We want to do, I can raise that up. We can do e to the fourth, e to the negative 3.7, and 2,500 times e to the 0.6. Okay, and again, I'll switch screens. I'll show you how to type those in. Stop this share. Share me, back to my calculator, and clear all this out. Okay, to get to your E function, it should be the same on any calculator. You hit the second button, like the shift button, and you go find this lovely natural log button, LN, because look what's right above it, e to the x. So if I click that, look at that. I get e to an empty box. So for our first example, we're doing e to the fourth. I type that in and I hit enter. Look at that. And we are rounding these to 3 digits. So we're going to have 54.598 for the first one. Then again, second, e to the negative 3.7. Enter. To 3 decimal places, 0.025. And then, typing in the last one, you type it in just like you see it. 2,500 second natural log. You get e to the 0.6. Like I said, type it in exactly how it's written on your paper. Enter. 4,555.297. There you go. That's it. Let's say that you don't have that math print, so I can go classic here. And let's say you hit your E button and you get something like that. Totally fine. You do the same thing. I'll type in 4, close parentheses. I'll type in negative 3.7, close parentheses. I'll type in 2,500 second e to the 0.6, close parentheses. That's it. As easy as it can be. So that should be calculator input on everything. Okay, cool. Stop share. Back to you, Robert. Oh, thanks, Robert. Okay, perfect. There's our answers right there. Okay. All right. So now we come across one more exponential property. Here is one more equality property for exponents. If a to the m equals a to the n, so if you have the same exponential base on both sides, then you can set the exponents equal to each other. Then m will equal n. And this property, this equality property, helps us solve for the given variable. So we will use this property on the next examples, just like this one. All right. So bring this down. So using this property, using this new property, well, first thing I notice is I have a base of 2 on the left and a base of 2 on the right. Since the bases are equal, this means that I can set these exponents equal to each other. So I take these and I come down here and I have x minus 4 equal to 3x plus 7. And all I have to do is solve for x. So let's say minus 3x plus 4 plus 4. I get negative 2x equal to 11. That's canceled, right? Okay. And then all I have to do is divide by negative 2. And x equals negative 11 halves. And sure, since you're business majors, you could convert it to decimal if you wanted. 11 over 2, negative 5.5. There you go. That's it for that one. Okay, do it again. 8. 3 to the 2x equal to 27 to the x minus 1. Well, we notice that the bases are not the same, but we can fix this. So our question is, can you make 27 into a base of 3? That is, yes, we can. So the way, when I say make 27 into a base of 3, I'm just telling us to rewrite 27. So let me show you this little chart over here. 3 to the first equals 3. 3 to the second equals 9. 3 to the third equals 27. This means that we can rewrite this 27 as 3 to the third. So that's what we're going to do. So I will rewrite this as 3 to the 2x equal to 3 to the third. That's 27. But now this 3, this exponent of 3 is now going to multiply the exponent that was there already. So we're going to get 3 times x minus 1. There you go. We have fixed it, and now we have the same base of 3 on both sides, which means you can now set your exponents equal to each other. And solve for x. So 2x equals 3x minus 3. Move 3x over, move 3x over, and you get negative x equals negative 3. Therefore, x equals 3. That's it. save that there for you. Okay, 9, same thing. Number 9. 9 to the x minus 1 equals 27. So once again, these bases are not the same. So what we have to do is find a common base. And the common base between 9 and 27 has to be a base of 3. Because 9 and 27 are all multiples of 3. So this means that we can actually use this chart that I made over here on the left. So this means that 9 can be changed into 3 squared. So we'll get 3 to the second times x minus 1 equal to, and we did this already, 27 can be changed into 3 cubed. So we get 3 to the third. Okay. Now we have the same base. Set your exponents equal to each other. And we get 2x minus 2 equal to 3. Plus 2 plus 2, 2x equals 5. Therefore, x equals 5 halves, or 2.5. There you go. That's how you solve exponential equations. Okay. Like I said, we're going to see the number e again, because now the next part is dealing with growth and decay applications. So for exponential growth, you see that we're given these 3 equations, which are all exactly the same, just different notation. Y equals c times e to the kt. C is your initial amount, just like on the second equation. N equals an initial times e to the kt. An initial is your initial amount. Third equation, A equals A initial times e to the kt. A initial is your initial amount. All right, there you go. Now you have an exponential function with the base of e on all of these. So now you see that all of these have e to the kt, e to the kt, e to the kt. So if k is greater than 0, what we're saying here, if k is greater than 0, this means that our function represents a growth rate. So if this little k there is greater than 0, it is a growth rate. If our k is less than 0, then look down below, it represents a decay rate. Okay. Well, we hope our money doesn't decay like it is doing right now in this pandemic. Oh. Okay. T is in time, and Y or N or A are the final amount. That's it. And all 3 functions are exactly the same. The reason they have different notations because they're used for different problems, but they all mean the same thing. Okay, perfect. So that is an exponential growth equation, which means that we come down to the next example. It says An exponential population model for Ethiopia in 2008 was 83 times e to the 0.032 t, where t is the years since 2008. Does this model represent growth or decay? Growth or decay? Okay, well, does it represent growth or decay? Well, look at the k value. Here, we have to see this equation as, as p equals, what are we going to say for population? P initial times e to the kt. Well, looking at this, 0.032 is my k value. So, coming back over here, since k equals 0.032, this is also positive. This will represent a growth model. This will represent a growth model. Okay, right, because this is positive. Okay, then it says, using this model, what is the predicted population for Ethiopia in the year 2020? Well, with that being said, T is the year since 2008. So what would you plug in for T if it's the year 2020? You would plug in 12, right? So we would write P equals 83 times e to the 0.032 times 12. And you type it in your calculator just as I wrote it. All right, 83 times e to the 0.032 times 12. And we get 121.86. Okay, so we're not really given a number, like we don't know if this number is in the millions, billions, trillions, but we know by this population model that our population will definitely grow. So yes, this number could be in, let's just say, millions. Question mark. Okay, cool. All right. Last page. Okay, here we get into some important concepts which are going to help lead us into chapter 3, which is heavy on calculations and knowing exponential functions and knowing logarithms. So logarithms are next after this lesson. Okay, so here we come across the compound interest formula. So some definitions real quick. Interest is the fee paid to use another's money. Interest rate is computed as a percent of the principal over a given period of time. And compound interest is interest paid on interest reinvested. So this is the formula we will use to represent compound interest on an investment or a loan. So putting this together, we are given the formula A equals P times 1 plus R over M to the MT, where A is the final amount, P is the present amount, the beginning amount, R is the rate, M is the number of compoundings a year, and T is time in years. All right. So this is called the this is just called compound interest formula. So we will use it to solve the next problem. So this one says, if 11,000 is invested in an account paying 10% compounded monthly, how much will be in the account at the end of 10 years? Round to the nearest cent. Okay, so what I always love to do is label everything we're given. So the very first thing it says, $1,000 is invested into an account. That is giving us the beginning amount. That is giving us the present amount. So what we say is P equals 1,000. Then the next piece it's saying is that we are given a rate of 10%. So my rate is 10%. But remember, you always must convert percent to decimal. 0.1 represents 10%. Then it says we are compounding this money monthly. So compoundings go based on a year. So when it says we compound monthly, how many months are in a year? That number will be 12. Then the very last piece says how much money will be in the account at the end of 10 years. So this says time is 10 years. 10 years, 12 months. So this means that your $1,000 is getting investments paid every single month for 10 years. Now that sounds nice. That sounds like we'll be rich. Let me tell you now, it's one big lie, okay? So everything's a lie, right? Yeah, PEMDAS was a lie. All right, so now let's plug it into the formula above. All right, so we are gonna get A equals the present amount, which is $1,000, times 1 plus my rate of 0.01 over my compoundings of 12. And now, all of this is being raised to my compoundings, 12, times the amount of years, 10. There it is. Now, type this in your calculator. I will show you how. And I always write participant. I always write parentheses for a reason, okay? So let me screen share mine. Let me go back to my calculator and boom. We're gonna type in exactly what I wrote down, exactly how I wrote it. So we start with 1,000. Start a parentheses. 1 plus fraction button. 0.1 over 12. Close parentheses. Raise it, parentheses, 12 times 10. Close parentheses. Just like that. Enter. And after 10 years of investing $1,000, we have only made $2,707.04. Well, hey, in 10 years, if I subtract this from the original investment, in 10 years, we made $1,700. Wow, right? We made $1,700, which means if you divide that by 10, you made $173 every single year. Well, that's free money. But in 10 years, you only made $1,000? Nah, we need to find a better way to invest, right? Get you thinking now. How do you invest better? And one of the ways to invest better is just don't put one chunk of money in. Keep putting money in on top of that chunk, right? So you put $1,000 in, like, okay, well, I have 25 bucks to spare. Put in 25 bucks every month on top of that. Or if you can't do it monthly, or if you can do it more than monthly, you can put 25 bucks in a week, every 2 weeks, every month. So the more money you put in, the more return you'll have. Unless coronavirus comes again, then we all gonna be broke again. Okay, that's how you type it in your calculator. Let's say you didn't have the fraction button, right? You would type it in as 1,000 times 1 plus 0.1 divide 12 raised to, and here you can still do parentheses, 12 times 10. Enter. Same thing. Just a little different input. Okay, perfect. All right, back to me. Let's see, screen share, yes. Go to me, and broken, and there we go, we're back. Okay, so that is compound interest. So that's how that works. Label all the pieces, plug them in, learn how to type it in your calculator. The next formula is what I keep trying to say. Continuous compound interest. Continuous compound interest is given by the formula A equals P times E to the RT, or we refer to this equation as your best friend. Your best friend's name happens to be PERT, okay? PERT is continuous compound interest, and this formula calculates your money growing every second, every minute, every hour, every day, every week. So you think that we would be so rich using this formula. Again, that is a lie. Because you're like, man, my money's making money every second, every minute, every hour. I should be rich in no time. No, sir. No, no, no. It all honestly depends on the amount of money you put in and the rate you're actually getting. So it doesn't have to be a lie if you're rich. Just saying. Okay. So just like the one above, for PERT, A is the final amount, P is the beginning amount, R is the rate, and T is time in years. Okay. All right. So with that being said, label everything. We are investing $1,000. So again, that is my beginning amount. We are getting a rate of 10%. So that is 0.1. We are compounding continuously. So how much will be the account after 10 years? Time is again 10 years. Okay. Plug all this into your PERT formula, and we'll have A equals 1,000 times E raised to the 0.1 times 10. And let's go to my calculator. Back to you, Robert. Thanks, Robert. I'll take it from here. Am I going crazy? Yes, we all agreed this. Okay, so typing this in, 1,000 second natural log, get you to the E button. 0.1 times 10. Oh, I forgot parentheses, but hey, it's all still in the exponent. But if I want proper notation, let me do that. Second, insert parentheses. There you go. Like I said, type it in exactly how we wrote it. Enter. And after 10 years of continuous compound interest at 10%, we only come out with $2,718.28. It's definitely more money than the problem above. It's more money by $11, but still, after 10 years, you still make $1,700, which, hey, it's free money. I'll take it. But again, we need to find a better way to invest. We don't put money in and just let it sit there. We keep piling money on top of our money. The more money you have, the more investments you're going to get back. So that's what you want to do. All right, guys. Stop share there. Back to me again. There we go. There we go. There we go. There we go. Going, 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 going. There we go. And there's our answer. Okay. Perfect. Okay. All right. So that is it. That is exponential functions. Thanks, guys.